yeah, my thesis is mainly about how can you use multiple graphs in learning. How can having more than one graph improve the learning capabilities of some architecture? And in this case, we consider two different graphs that will be used to define the underlying support of the input and the output of a graph neural network. But let me start with what I'm going to talk about. It's really simple. It's some. I will introduce the topic, then I include the problem formulation together with what we are proposing to do to solve it. Some numerical results of this first part of this first proposal to solve this problem. And then connection with other fields, more precisely canonical correlation analysis, self-supervised learning, and how can we use this architecture or some similar to it to solve this problem, and some numerical results also of this part. So not taking too long, but yeah, you already know that graphs are everywhere, and that with the constant amount of data that is generated this day, we need some supports. Some new supports, some new ways to process this kind of data, but more precisely, sometimes the current tools like graph neural networks are not enough. We have architectures that model the input, the output of the data differently with different graphs, and we need to exploit every bit of information we can. In this work, we deal, as I said already, with graph neural networks where the input and the output are defined on two different domains. Also, really quick, some preliminaries more to establish the notation than to tell you what's a graph. Basically, we denote by G a graph, denoted by a set of nodes, set of edges, and the adjacency matrix A. We define a signal on top of a graph with the vector X. We define the graph shift operator as a matrix that defines the local structure of the graph. It's a generic matrix. We can use the adjacency, the combinatorial graph Laplacian, but we'll define this graph shift operator. We'll use it to define the graph neural networks. And the idea of graph signal processing is to exploit the structure of the graph shift operator to efficiently process the signals. And there has been a lot of advances in the recent years from linear processing. And the most recent advances are more related to the deep learning and graph neural networks. So, but usually, or in general, graph neural networks usually deal with use graph signals, but either the input is a graph signal defined on top of a graph G, and the output is a scalar, a class in graph classification setting, or the input may be a graph signal and the output is a graph signal defined on the same graph. We are looking to find some node embeddings, but the nodes are always of the same graph. And we can use these embeddings for some kind of node classification task or whatever. But the idea is that we deal with a single graph in both cases. There are several other architectures. Also, there are several works that deal with different graphs, but oftentimes they have limitations on regarding that the node set must be the same, and then we can construct different edge sets or things like that. So there's like some kind of similarity. In this work, we consider two graph signals, one defined on top of a graph Gx that will be called input graph, and will be the graph where the input signal to the graph neural network is supported. We'll call this signal X, and this graph will have n nodes with graph shift operator Sx. And we have a completely different graph that can have a completely different node set, completely different edge set, and completely different topology with m nodes where the signal, the output signal, is defined. And we have the graph shift operator Sy. I'll try to motivate later why this architecture makes sense and what applications we could have it in the numerical experiment session. But the idea here is to find a nonlinear mapping in the form probably of a graph neural network architecture that learns the mapping between X and Y, leveraging the information in both the input and output graphs. So we want to find a mapping from this X that lives in Rn because it's supported on Gx, And we want to find the output that it lives in Rm because it's supported on GY. And probably using a graph neural net. So here we cannot use like a usual GCNN graph attention network because the output of these layers are defined on the same graph. So we need a way to do the transformation from the input graph to the output graph. The idea we had is, okay, let's do it in the latent space. Let's learn some embeddings using the input graph, perform some transformation in the latent space, and then learn some or use a second step where we use the output graph to transform these embeddings. So in this setting that we have some embeddings, we divide our architecture into three parts, into three steps. We first process the input signal using a function that we'll call psi(x) to learn some embeddings that are still defined over the input graph. They are graph signals defined or node embeddings for each node in the input graph. Then we perform a transformation function that transforms the embeddings from the input graph with n nodes to the output graph with m nodes. The embeddings in the input graph will be called set x, and the embeddings on the output graph set y. And then we use the output graph in the final transformation layer, let's say, that we'll call psi y to transform these embeddings or to use the information in the output graph to transform these embeddings. So we will have that the signal is divided into three steps. We use the input graph, transform, use the output graph, let's say. And to do to implement these steps, psi(x) and psi(y) can be implemented using standard GNNs. They are using signals defined on the support of a graph. We can use some GCNN, some graph attention network, whatever architecture of your choice, to learn these embeddings, and from this, from set y, to learn the output signal. The key here, or the idea, or the new thing, or the complex step is on psi set. How do we do this transformation between graphs? And it will be covered later. But in the end, just to reinforce the idea, we are just learning the mapping as the composition of these three functions, where we first apply psi(x), then we apply the transformation psi set, and then psi y in the last step. The parameters of the three functions that are grouped in the parameter sets theta x, theta y, and if psi sets has some parameters theta set, can be learned through backpropagation as long as this function here is differentiable. We could backpropagate the gradients here because this is a standard GCNN. If this is differentiable, we can apply the chain rule to backpropagate the gradients here, and the same here. So we can learn all the parameters jointly, just with the assumption that this function is differentiable, that we'll see next that it's pretty doable. But again, coming back to the transformation function, the key of this approach, or the contribution that we introduce in this work, is this step here. How can we design it? Well, what we are going to do is not to propose a single subset, but to design some taxonomy, some family of functions that we can use to do this transformation between these embeddings defined on the input graph and these embeddings defined on the output graph. So we have several design choices. The first one that we can think of is, okay, it will be specific to the task that we are trying to solve, or it will be agnostic. It will be a generic transformation function. For example, let's imagine that this is an application that I'll explore later in the numerical results, but let's imagine that GX is a coarse version, a cluster version of GY. So this will be something like an interpolation task. We are trying to, from a coarse representation, find the representation on the larger graph, let's say. We could say something like, okay, if I know that this node here corresponds to these two nodes here that are grouped together into one, we could say, okay, then I do the transformation by simply copying the embeddings from this node into these two, let's say. So we will be like considering some extra information, some domain knowledge to implement this transformation. Or we could propose also something that is agnostic to the underlying task, that can be used in any setting, that we'll see also some examples next. The next design choice is, okay, are we going to learn it from the data, this transformation, or are we going to just fix it before starting the processing and use that? Well, if it can be learnable, we can use, again, the gradient descent that we were using to learn the parameters of the GNNs, and backpropagation to learn the parameters of this function. If it's fixed in advance, like for example, the example I just gave of the domain knowledge task that we are solving, then it will be, it won't be learned. It won't have any parameters and it won't be learned. The last design choice I'm going to propose is, okay, are we dealing with a linear transformation or some kind of more complex transformation? Just in this case is to think about the complexity of this step. In the linear case, the most general case, we will have to work with the vectorized version of the embeddings, but we will have here a huge matrix. Why? Because this f set y is the input, is the size of these embeddings, and f set x is the size of the set x embeddings. And this can be designed. We are designing the graph neural network. We can choose what's the dimensionality of its input and output. But m and n usually come fixed by the underlying task. It's the sizes of the graph. So we cannot decide them. If these graphs are somehow big, this matrix will have a huge number of parameters. And we could have a scenario of overfitting. We could be overfitting to the underlying task because we have a lot of parameters. But still, we can try to put some structure into the transformation, as I will explain next. And if we want some, I don't want a linear transformation, this is too simple, we could go to more complex transformations that are still differentiable, as I said before, in the case of, for example, an MLP or something in that sense, or something that uses the information in both GX and GY. We could maybe implement something like that. So, okay, I talked about giving some structure to this W. Let's see how. The first option, again, I'm going to give a couple of options that we could use, is to design W as a low rank matrix. We design it as a product of a tall matrix times a fat matrix, and we learn, instead of W, we learn these two matrices. And we will be, in turn, reducing the number of parameters of the architecture if this K is small, if this rank, the rank of W is small. And these two matrices can be learned alternatively. We fix one, apply gradient descent on the other, and the other way around. Okay. We could also give W some kind of Kronecker structure like follows here. Why? Because of this property here that, the vectorized version of the product of three matrices can be expressed as an expression that involves a Kronecker product. We will be computing a set Y by left and right multiplying by two matrices that are smaller than this W. Instead of using the vectorized version, that is the most general case, here we say, okay, I'm going to multiply by left and right by two different matrices. So what we will be doing is, by left multiplying, we'll be combining the information across rows of set. So we will be combining the information across nodes. And with right multiplying, we'll be combining the information across features. And these two matrices can be either fixed if we have some domain knowledge to create them, or simply learned through backpropagation as well. And also, as there is the product of two matrices, as in the low rank case, we could use some kind of alternating algorithm to learn them if we want. And the last example of a permutation matrix, a transformation matrix that has some linear structure is a permutation matrix. It's okay, I rearrange the cells from set X to form set Y, or something like that. These are like three examples of how can we impose linear structure. And now we're going to see a couple of actual implementations of these kind of functions and how can we use them. So we are going to provide two examples that are easy to implement and that can be applied in any situation. They are not using domain knowledge. The first one is doing the transpose. this requires to set the output size or the number of features at the output of the input GNNs to m, to the number of nodes in the output graph, and the input to the psi x, psi y in GNN, it will be n, and we simply transpose our transformation matrix. And in turn, what we will be doing is to perform some equivalence between node signals and features. So if in the input, the feature 1 for all the nodes, the graph signal that corresponds to the feature 1 will be transformed to all the features in the first node of the output graph, and the other way around. And this will be like, okay, I'm going to do a permutation matrix. I'm going to rearrange the cells of set X to form set Y. The second simplest transformation function that we came up with is, okay, I just need to transform from one graph to the other. So I need to transform the domain of the number of rows, let's say, from n to m. In this Kronecker structure that we propose by left and right multiplying, the only one that is necessary actually to perform the transformation is the left one. The right one, we can set it to identity, and we still can work with that. Will be that the output size of the input GNN is the same as the input size of the output GNN. That's perfectly fine. And we left multiply by some matrix that we can learn through backpropagation. So this will be like two examples that we could use to implement the transformation. Now, some kind of characterization of this graph neural network architecture. We have first defined what are the 3 steps. We have defined how can we define the transformation, how can we characterize it. In general, GNNs or standard GNNs like GCNN are permutation equivariant, which means that if we permute the input and the graph shift operator, we get a permuted version of the output for any permutation matrix. We cannot tell this in our setting because the input and the output are defined on different spaces. So we cannot talk about this property in our setting. But what we could try to do is, okay, what if I permute the input with some permutation matrix Px, we permute the input GSO with the same permutation matrix, and permute the output with a different permutation matrix operating on the output graph, Py, we can say that the output can be this Py, let's say, permuted version of the previous output, of the output we had. And this is fulfilled as long as the transformation functions fulfills this, that if the input is permuted by Px, the output will be permuted by Py. This can be easily proved by considering that the inverse, that this is an unitary matrix, this inverse is transpose, and it's the closest we can get to the permutation equivariance property in this setting. And this can be achieved more or less easily. For example, in the transformation function that we propose with a learnable weight matrix, we will have like just to permute the weights as appears in the slides with Py times Wn times Px transpose to achieve this property. It's a bit weird, but we can get this kind of generalized, let's say, permutation equivariance or applied to our setting with this simple rearrangement of cells. Okay, I've designed the architecture. I've designed some transformation functions. I'm going to now present some numerical results for this part. The first one is more of a sanity check, is, okay, what is the easiest way you can get 2 graphs from for a task? And that was what, like, okay, I'll pick a graph, in this case, the Cora graph data set, and I sample 2 graphs from that. We use a snowball sampling, that is basically to get a subgraph, we randomly choose a node, we consider its neighbors, and the induced subgraph by these nodes. And the idea is, okay, we sample 2 subgraphs using this method, and using the features on the first graph, we try to get the labels on the second graph, on the output graph, using our architecture. And here we plot the accuracy over the test node set, where as we had some subgraph, we couldn't use the public splits. So we did some random splitting of the nodes in GY to consider it as a semi-supervised learning, as this is usually approached in the literature. And we represent the accuracy over the test node set as we increase the number of neighbors in this snowball sampling. As we increase more neighbors, the sizes of the graph, of the subgraphs, are larger, and there will be more overlapping nodes between one and the other. The graphs will be more similar, so we expect that the performance actually gets better as we consider larger subgraphs. And the lines are the following. We have IOGCN, that is the architecture we propose using a graph convolutional neural network for psi x and psi y. IOMLP, that is the same architecture but using an MLP, not using the input and output graphs, not using the graph structure. The W is the learnable transformation, that this one here, set y is equal to wn set x. T is using the transpose that we also introduced, and C is a domain-specific transformation that we implemented in this setting, as there are overlapping nodes. In those nodes that are overlapping between GX and GY, we copy the node embeddings, and the rest that are not overlapping on GY, we set them to 0. It's like a domain-specific using the knowledge that we know that there are overlapping nodes between GX and GY. GCN is the GCN operating with full information. Unlimited GX, GY, and GXY is like we use the GCN with full information, but we mask every edge and every feature for the nodes that are not in GX or in GY or in the combination of both, let's say. So this is what can we do with a simple GCN in this setting with the same amount of information. And we can see that, okay, our architecture, that are these two blue lines using the W, the learnable transformation and the transpose, work pretty well, close to the GCN with full information. The GCN with limited information and the overlapping, let's say, transformation function actually increase or get benefited when there are more overlapping nodes, as was like normal, let's say. And yeah, in general, we are able, with our architecture, we are able to perform close to the GCN with full information, even operated on this limited information scenario. So it took me a while, but it will be useful for later. In the second case, I'm going to talk about an example I already provided, where GY is a fine representation of whatever it's in GX. So the GX is a coarse version or a cluster or a selection of the nodes of GY. And we want to map the signal from GX and GY. I like to think this as a brain network problem, where GX is, okay, we have 10 sensors in the brain, and GY is, okay, we have 1,000 sensors. Putting 1,000 sensors is very costly. How can we use the information from these 10 sensors, let's say, to get the information with 1,000 sensors using a GNN? We don't have to put the sensors itself. We measure with 10, and we do this mapping, let's say. In the first case, I'm going to provide two numerical examples of this interpolation case. The first one is with image interpolation. We create a graph where the nodes are superpixels of the image, cluster version of the pixels, and the graph is a region adjacency graph. Two nodes are adjacent if they are two nodes are connected if they are adjacent in the image. The top row is the input and output of our network, basically the graph using the coarse representation, the input graph using the coarse representation, the output graph using the fine representation. And this is, okay, we consider as signal on top of this graph the mean color of all the pixels in each superpixel, let's say. And the output, the target, is the same, but in the fine representation of the graph that we can see a lot more details. The bottom row is actually the results. This is with our architecture. This is a convolutional neural network operating on this image that we can see that just copies basically the input image. KNN, what it does is, okay, I look for each node in this here, for each superpixel here. I look for the closest superpixel here and we do some kind of KNN aggregation. And IOMLP is the input-output, but without using the graph information. We deal with semi-supervised tasks. We assume that we know the information in some of the pixels and we don't know it in others. And we can see that IOMLP is actually doing some overfitting on the pixels that we know. And IOGCN, even if it's not really pretty, is the one that is getting more of the details of the output image better than the alternatives. And yeah, this is basically, okay, measuring the mean square error, how we perform as we increase like the relation of nodes in the output and input graphs. And basically we see that our architecture is the only one that is able to actually denoise the graph and perform better than the line mean X that is just, okay, I copy the input, I do nothing, let's say. And the architecture using the graphs is actually able to improve that, to improve just using the input. Next experiment is something very similar in the interpolation setting, but with computational fluid dynamics and fluid flow prediction. We have that in this kind of settings, we mesh we create a mesh of the surface we want to characterize. And the finer the mesh, the more computationally costly the simulations are. So using a coarse mesh that we can run the simulation fast, can we improve the performance can we get the data in the fine mesh, let's say? And the answer is more or less yes. With our architecture, we're getting the lowest error in both interpolation and generalization. These two experiments are, okay, we have a training set of some time samples, and we have a test sets of a different time samples. Interpolation basically is the train and test contain more or less the same distribution of data. The generalization is in train, we don't include shocks, and test we do include shocks. So it's like the distribution between the train and test data sets change, let's say. And in both cases, our architecture using both the learnable transformation and using some domain-specific transformation is able to perform the best. And we actually see this qualitatively, that we are able to get the phenomena that we see, like in both the front and the trailing edges of the profile, of the NACA profile. So it's actually a sanity check that we are actually getting a good result. And yeah, I don't know how I'm on time, but okay, 5 minutes. Real quick, I wanted to link this with other works, more precisely canonical correlation analysis and self-supervised learning. Canonical correlation analysis seeks to find, we have two views of data, X and Y, and we want to transform them to a space where they are maximally correlated. This is defined by this function where sigma is the cross correlation matrix, and subject to that, these transform views are orthonormal. Okay, so it's like, okay, I want to find alternative representation of the data in a different space, such that these two are maximally correlated. In the deep setting, it's like, okay, here we computed our transform views as X times U and Y times V. Okay, instead of doing that linear mapping, we use a neural network, and we simply try to maximize the correlation between the outputs of the neural network, where this while also ensuring that the output of the neural network is orthonormal. And in a slight different reformulation that was proposed in the literature, what they did is, okay, instead of maximizing the correlation, I minimize the distance. That's basically the same. And we include some term in the objective instead of putting it as a constraint that we know that dealing with constraints in deep learning is complex. We put some term in the objective that is called stochastic decorrelation loss to try to decorrelate the outputs of the neural networks, let's say. And they solve this problem this way. What we did is, okay, our architecture more or less is similar to this. How can we adapt it to this setting? it's okay, I'll apply, we have two views of the data defined over different graphs. We apply our input GNN and our transformation function, and we applied the inverse of the output GNN, that in turn it's another GNN. We don't have to compute any inverse or anything weird. And we try to maximize the correlation between these two. And this will yield us with an alternative representation of our data, let's say, that we can use for a downstream task. So don't get too scared about the formulation. This is simply saying, okay, I compute the input transformation, we compute the input GNN, the transformation function, and we try it that it's maximally correlated with the output transformation, let's say. And we try to solve it using this loss function because it was easier to implement, let's say. And why do we want to do that? Because in the self-supervised learning field, what they look for is, okay, I want to find alternative representation of my data that contain as much information as possible, so that with this alternative representation, I can train a simpler classifier, let's say a logistic regressor or something like that, that with a very limited number of labels is able to perform more or less well. So in this case, as we are implementing a simple classifier, we need that the information in these alternative representations encodes both the graph structure and the data structure, let's say. And that's what we did in the next experiment. This is the experiment of this self-supervised learning part. And what we did is, okay, we have an input graph, G, in this case, the Cora and Sightseer citation networks. We get two graphs. Gx is G, but with some edge drops and feature mask. So we have an imperfect version of this original graph G. Gy is a subgraph. We consider that we know a subset of the nodes, but with perfect information, with all the no edges dropped, no feature mask. And we try to use the information in these two, the one that has the complete node set, but not the complete edge set and mask and features, and the one that has perfect information. And what we find is that the alternative, the CCA-SSG, that is the self-supervised learning version of GNNs, that is the state of the art, its performance when there are not very, sorry, I didn't say, but the x-axis marks how many edges and features are maxed in GX. So how imperfect is actually GX. And the performance of the state-of-the-art architecture drops substantially as we have more imperfect information, let's say, while the performance of our architecture more or less remains stable until we do have a very high number of edge drop. This is almost the empty graph, let's say, that the performance starts dropping a bit, but not as fast as the alternative of the state-of-the-art. And something similar happens in both Cora and Sightseer datasets. And both of them obviously work better than the MLP that does not use the graph information. And yeah, I'm almost done. Closing remarks. So what we did is to propose a novel neural network architecture to learn a mapping from a signal defined on some input graph to the output defined on some other output graph. And to do this, we propose it to split it into 3 steps. First, a graph-aware neural network from X to the latent space. Then we perform this transformation in the latent space. And then another graph-aware neural network from the latent space to the output space. And we can learn the parameters jointly, efficiently, through backpropagation, etc. Then the key step in our approach is step 2, obviously, because these are just standard GNNs. So we propose a taxonomy according to several design decisions. How can we design this transformation function? And we did some analogies with other fields like canonical correlation analysis and self-supervised learning to use this architecture or some relationship from this architecture to learn this alternative representation. And thank you very much.